Hey guys, welcome to Castle Unit 6, Activity 5 for the day of the 27th of April, 2020. Okay, we're starting to get pretty deep and we're almost done now with this unit and with our treatment of electricity. This will be the last of it, so we'll be done in the next week or so. Okay, so this activity is the first activity in the second part of Unit 6. The first part of Unit 6 was covering things like voltage, pressure difference, and resistance, how we measure those and how they're related to each other. This second part of Unit 6 is going to cover how those three things are related to electrical power. Okay, so we're going to go ahead and start our discussion of energy and power with electricity, and that'll be what will finish us out this year. Before we jump right into this activity, I want to ask just a couple of questions, and obviously I am going to answer those questions as well. The first question that I have is, which bulb is brighter? And what we know about a circuit like this one, where we have two bulbs in parallel, a round bulb and a long bulb, one with low resistance and one with high resistance, the round bulb, or the one with the smaller resistance, is going to be brighter, because it's letting more charge move through it. Now the bulb lights because there is charge moving through the filament, and that moving charge generates heat. Okay, so there's energy transferring into that filament in the form of heat, and then out of that filament again as light. So the heat causes the filament to glow. And so what we have happening here in the bulb is a transfer of energy. And obviously, if it lets out more light, if it's brighter, it's using more energy than the one that is not as bright. Okay, I'd like for you to go ahead and make your predictions of what you're going to see in this circuit. Okay, so go ahead and take out your Unit 6 Activity 5 worksheet, and on the left-hand side, go ahead and start making your predictions. First, label the values of the resistors. As you see here, I have made each long bulb, the high resistance ones, 50 ohms, and each round bulb, 10 ohms. Okay, so here are my round bulbs, quote, and here are my long bulbs, the ones with high resistance. Okay, next I want you to rank the pressure differences across each bulb in order from largest to smallest. You should already kind of know how to do that. Okay, we know that in parallel, both bulbs will have the same pressure difference, and in series, the one with the larger voltage will be the one with the larger resistance. So this one is obviously then going to have a higher pressure difference than this one. Give you a second to do that. Okay, next I want you to rank the flow rates through these four bulbs from largest to smallest. We know that in parallel, one of these is going to have a higher flow rate because it has a lower resistance. And in series, these are both going to have the same flow rate. So go ahead and do that as well. Finally, I want you to predict which one of these bulbs is going to be the brightest, and then rank them from brightest to dimmest. Okay, so one of these four bulbs is going to be brightest. The other ones then are not going to be as bright as that one, obviously. And while you're predicting the brightness, remember that you're also essentially predicting the power, how much energy each one is using. Okay, let's go ahead and test our circuit, big air quotes there. Taking a look at the now connected circuit, I see that definitely this bulb right here, the low resistance one on the left, is definitely my brightest bulb. Okay, so on the right side, where it's asking you to record the relative brightness, list them in the chart from brightest to dimmest, to record the pressure difference and to record the flow rate. Let's go ahead and do that together. The one that is the brightest is this bulb right here. Okay, we can count them from, starting from this one to the right. That would be a normal way to count. 1, 2, 3, and 4. Bulb 2 is definitely the brightest. That one has a resistance of 10 ohms. We see that the flow rate, or the current going through it, is 0.9 amps. And since it's hooked up in parallel to the battery right here, the pressure difference across it is 9 volts. The next brightest bulb, and it's kind of hard to tell since they're so far apart, it's either this one or this one, but I think that this one, our lines do look a little bit longer. And that one has a pressure difference of 9 volts as well, since it is in parallel with that battery. And it has a current going through it of 0.18 amps, which is obviously less than this one. The next brightest bulb looks to be this one then, bulb 4, which has a resistance of 50 ohms, a pressure difference of only 7.5 volts, and a current, or a flow rate going through it, of 0.15 amps. You see that up here. I just have one ammeter that measures both of these in series. That means that the dimmest bulb here, the one that's essentially almost not lit, has a flow rate also of 0.15 amps. And since these two in series have to have a pressure difference that adds up to 9 volts, it must have only 1.5 volts across it. Okay, so that should take care of your observations that you have on the right side. Let's go ahead and talk about some of the stuff that we see happening in here. Okay, here are the very key, the very, very important observations that we need to have made here. The first is that the bulbs on the left that are in parallel have the same pressure difference. But since they have a different resistance, they have a different flow rate, and therefore they have a different amount of energy being transferred. The one with the lower resistance, and therefore the higher flow rate, has a higher brightness. We've essentially done a little tiny experiment here, like a mini experiment, where we have held the pressure difference, or the voltage for these two bulbs, constant. But we have changed the flow rate to see how much energy they use, which one is brighter. So obviously we see that higher flow rate corresponds to a higher brightness and therefore a higher energy use. The bulbs on the right, however, are in series, which means that they have the same current or the same flow rate, but different voltages. So we've done another one of these sort of micro experiments with the bulbs on the right, where we've held the flow rate constant, but we've changed the voltage in those two bulbs. And we see that the one with the larger voltage out of those two is brighter. Therefore, the one with the larger voltage is using more energy. So we can conclude from those two kind of small experiments, those mini micro experiments within an experiment, we can conclude that higher flow rate corresponds to higher energy use. And we can also conclude that a higher voltage also corresponds to a higher use of energy. So both of those statements are true. Both the voltage and the flow rate are going to determine how much energy is used by a bulb. Some final points that I need you to take down on the bottom of that sheet. The amount of energy that's transferred again depends on both the flow rate and the pressure difference across the resistor. If the pressure differences are the same, then the one with the greater flow rate results in greater energy transfer. Similarly, if the flow rates are the same, then the one that has more pressure difference, more voltage, is transferring more energy. And obviously, the more energy that we put into a light bulb, the more light and therefore also heat it gives off. So more energy, more light, more heat. Okay, and that should be pretty basic. Since I still have a couple of minutes left, I'm going to go ahead and put this electrical power notes on the same video so that we can keep that down for you. Okay, so I want to talk about then electrical power and how we define it. This is based on reading C6.1, which I don't really feel the need to give you since I'm giving it to you here. The question is, what is power? And remember, the power from what we learned in Unit 8 is the rate that energy is transferred in or out of a certain energy account. In this case, we are transferring electrical energy from the battery into light energy or heat energy. And again, energy is the stuff, this conserved quantity that causes physical changes when it's transferred. In this case, the physical change is in terms of light and heat. Energy is being transferred to the bulb from the battery, so the power input is the battery, the power output is the bulb. And in this activity, we just showed that power is dependent on two things, the current and the voltage. And those, of course, are both dependent on the resistance as well. Okay, so we can probably make a couple of different equations based on that when we get that far. In Unit 8, we defined the units of power as watts, where 1 watt is equal to 1 joule per second. That is, a watt was defined as 1 joule of energy being transferred in 1 second. That applies very directly to mechanical power, where we were talking about energy in terms of joules, but it's refined a little bit more in electrical power because we don't typically talk about exactly how much energy is being moved in what amount of time. What we're usually talking about is voltage and current. So we are kind of refining our definition for electrical power to say that when 1 volt of pressure difference drives a 1 ampere flow rate through a bulb, the rate of energy transfer, or the power for that bulb, is defined to be 1 watt of power. So we have 1 watt if we have 1 volt and 1 ampere. That's how all of those units are going to be defined here, so that 1 watt of power, 1 joule per second, is going to be equal to 1 volt's pressure difference driving 1 amp of flow rate, which means that we must also have a 1 ohm bulb in that case. Okay, this is going to help us with the next activity, so make sure you do take some notes on the bottom of that sheet about unit cells and unit bulbs. A unit cell is an imaginary cell or battery that maintains a 1 volt pressure difference. And a unit bulb is that imaginary bulb that allows that cell to drive 1 amp of flow rate through it, which means it must also have 1 ohm. So a unit bulb has 1 ohm of resistance. A unit cell has 1 volt of voltage. And if we use a unit cell to light a unit bulb, the power is going to be equal to 1 watt. So if we have a small little circuit right here where we have 1 volt on our battery and 1 watt, 1 volt on our battery and 1 amp of current, we get 1 watt of power dissipated by our light bulb. Okay, so again, 1 watt in electrical power is defined to be 1 volt and 1 amp doing whatever it does. Okay, that's 15 minutes. Have a good day, guys.